Thank you for the introduction. So maybe first of all, I'd like to introduce a bit myself. So my name is Armin, and I'm a structural engineer as well. I'm managing direction of BiMOTiON, which is a subsidiary company of Sophistic. And our main work in Sophistic is to transport knowledge from BIM or Revit technology to Sophistic supporter and developer. So our main focus is definitely working on all that BIM stuff. And I like to connect a bit on the speech of Stefan, and I like to talk about one specific type of doing analysis in building, and in my eyes this is the future of BIM regarding design and code checking. So as Stefan mentioned before in his speech, we see that the challenge of our structural engineers is that we, on the left-hand side, we have a 3D model, as also seen in the speech of Carsten, is defined as a physical model normally. You start with the physical, and then you have to transport that model into a so-called analysis model. So it might differ from the physical aspects due to some eccentricity you like to neglect in your analysis. And at the end of the day, we like to have some detailing and drawings. So that's what we need to achieve. And during this process, so first of all, for sure we have to do analysis. And as Stefan mentioned, analysis could be done in different variations. So Stefan talked about 3D analysis, standard 2D analysis, or we can talk about 4D analysis, so all the time influence like sweep and shrinkage. And I'm quite sure that we have many, many other types of analysis we can do. And in my speech now, I like to focus on a completely new concept of doing analysis, and we call that concept the building manager. So what is the building manager? So if I can explain that in simple words, the building manager is simply an organizational unit for managing component dependencies in Revit. So if we take a look at the building, we have different parts of the building. We have columns, we have walls, we have beams, we have struts, we have slabs, and we have to understand how their components are connected to each other and how they work within this entire 3D system to bring the loads from top to bottom. So that's what we need to understand as a structural engineer. And we can have maybe tools that give us some proposals how the elements are connected, but I'm quite sure that at the end of the day we have to influence that connectivity of such elements. And I will give you some examples in the next few slides. So I think you are quite familiar with that building because we almost used this building because it's a quite simple building, and this building has also some tricky points like some beams which has to transfer some loads from the top floors to not downstanding columns anyway. So therefore it's a quite good example to show you how we can drive analysis in a different ways from Revit. So you see on the left hand side you see the graphic of the building, so with some linear elements like columns and beams, with some face elements like walls and slabs, and we have also some nodal points like the supports at the bottom of that building. And if you take a look at the right hand side, I've done a sort of explosion of that buildings. For sure this is not the, oh this was the wrong, sorry. For sure this is not the graphical representation of the building, but it's more a schematic representation. You see that I have exploded now all the elements and I tried to define some connection between the elements. As you see, we have at the top, we have a floor or a slab, could be one of that element. So this is not the entire building, to give you an understanding. It's only a part of that. And the floor maybe is supported by some walls, some columns, and we have to define the connection between these elements. So in a normal analytical model, this is defined by hinged or fixed connections or something like that, or something also non-linear connection between that. And this tool we call Building Manager should give you an overview of your connection between the elements. And maybe in the next slides I will give you also impression that you should have a possibility to change that connection, or to change the work takedown, the load takedown of these simple buildings. So what are the results, or what we can get out of this graphical here on the right hand side? And first of all, the best result is that we can understand what are the adjacent members. So if I take out from the 3D building a column, I see immediately that this column is maybe supported by a column downstanding, or maybe by a walls underneath this column, or maybe it does not supported by some wall below, because it goes directly to a slab and there is nothing underneath this column. So I can immediately understand these adjacent members, and this gives us also an advantage that we can do a sort of model check. So if some elements does not have any connection at certain points, maybe you get an unstable system, and you can immediately understand that with your schematic information of your building with this Building Manager. The next point is that we can immediately see which elements absorbs loads, which for sure is dependent on your load case. So now we have to think about in which direction we bring some loads into our model. And this is quite easy when you take a look at a 3D system, but if you like to extract a 2D subsystem, the system might change if you input the load from top to bottom, or from bottom to top, or maybe such a wind load from left to right. So therefore you have to be really careful creating a 2D subsystem out of your 3D system by not knowing about your load situation. So the next what we can read out of this schema is which items induces loads. So quite the opposite of the absorbing the loads. You can understand which element induces load to other elements or to your subsystem you try to extract from your 3D building. And as mentioned before, we can do this model check, and we can understand if a member is supported or not. And if you mix all these points together, you have a really, really good understanding of your building afterwards. And that's what we have to know as a structural engineer. As Stefan mentioned, we don't have to calculate the building, check the results, so we have to understand how the building is working by introducing some loads to this structure. So in addition to that, we immediately understand if columns in that buildings are in line, so we can also extract this entire column over the entire building, not only one part of this column, and we can influence and we can understand the connection behavior between all these elements. So maybe let's go to the next slide. And the next slide is quite the same as the last slide. You see at the right side again this schema, but the difference between the last slide is that now in this schema we have already applied a load. So you don't see any lines between the elements, you see arrows. So that means this is the load direction of your building. So as mentioned before, this schema now is dependent on your load case. So now we focus as first step on the vertical loads. This work? Check that on. Is this on? This on? Oh, okay, it's on. Perfect. So I have to go a little bit outside now to give you a better understanding of that. So as you can see here, we have the slab, which introduces loads into the adjacent elements like walls and column. And normally, as we have learned at the university, loads try to find the shortest way to the bottom, okay? So if we take a look here, you see that from the slab you get some load into the wall, and this wall is connected with an additional floor below and also with additional wall. And for sure now we have two connection elements, so two possibilities for the load takedown. Remembering that the shortest load should be the best one. Possibility for that the load goes over there, it's quite good, okay? So we can maybe exclude this load path. But that's not correct at all, okay? I will give you an example afterwards. So the main point here is that we can have tools that give you a suggestion of your load path, okay? And this could be a theoretical load path, even if this load path is not 100% correct, or maybe also not 100% of the load goes directly in the wall, maybe also some percent of the load goes in the slab, to go from the slab directly in the column. So I think you as a structural engineer has to do that decision, okay? So it means we can give you a suggestion of this load path and try to give users access to this load path. So give the user the possibility to interact and modify the load path. So as mentioned before, we will focus on a vertical load case because all the other one is quite tricky. So let's go to the next slide. So this is now more a graphical representation at the right-hand side of a possible situation where we have two slabs, we have three columns at the third floor, we have in the middle floor, we have a wall transferring these column loads to the columns below, and in between, for sure, again, we have a slab. So that might be simple. We bring some loads from top to bottom, and you see here on the left-hand side the graphical load path for the standard load case. So this is what the software maybe suggests you, and you can directly transfer all these loads from top to bottom, like the wall loads goes to the slab, and the slab transfers the load to the column, which I think in my eyes is not the correct way. But it is the shortest way. So this is definitely regarding length of the way, it's the shortest way, but not in terms of energy. So therefore, I think in this case, we have to change the load path, and this is what I like to show you now in this slide. So the simple possibility to change these arrows here at the left-hand side to not defining that the wall transfers the load to the slab and the slab will transfer the load to the adjacent column, we need to have the possibility that the slab is connected to the wall, brings the loads of the slab inside the wall, so bringing back to top. You see that is not the shortest way. And from the wall back to the column. And that's the main point, that we have the possibility to influence all these load takedowns. Okay? It's now your choice to understand the building, to move some load paths, maybe not 100% of that load paths, but you can also try to give a 50% over there, the rest over there. So it's your choice to drive the analysis as you like to have the result. As Stefan mentioned, and also my words, so we can define wrong and right as mathematicians, so we are almost modeling some not 100% perfect elements, and we have some small adjustments in our models. Okay, so let's move to the next slide, because the next problem is how we can extract now such an element and how we can define the supports, or how we can transfer the induced load to the supports of these elements. And there are many, many possibilities. So maybe let's talk about an element like a shell or a wall, and we have the possibility to apply some actions on that. And for sure, at the other side, we need some reactions. And as we learned at the university, we need the equilibrium. So we can define that all the reactions depends on all the actions with a certain function. And you have now also here the choice how you can transfer these actions to your supporting members. So first thing maybe is that we can do a finite element analysis of this shell. So we can support these elements, we can create a mesh, we can apply loads, and then we can run a finite element analysis to understand how many loads goes to the left support and how many loads go to the right support. The other possibility maybe, it's quite a simple one. We can have, maybe if this is a beam with 2 points as a support at the left and the right, we can take the left, the half of the loads goes to the left and the other half goes to the right. So we have many possibilities here also to drive this connection between all our members, and that's quite important. Okay, so that means, what's our workflow? The workflow is that we have a model getting from Revit. We can drive all the analysis, as Stefan has mentioned, like 3D, 2D, 4D. We would like to give the possibility also to have a completely new possibility to understand your building, combining 2D and 3D, get out some subsystems automatically, and maybe we like to do that directly in Revit, that you can, for example, select a column in Revit, do right-click, defining some groups for that column, so means select columns which are quite the same, which have the same geometry, quite the same loading, quite the same system. And then you can apply some group information to do a design for these sub-elements, okay? And then you can get an envelope of all that data. You can run the design for each element, and the result is that you get one subsystem as column design, for example, to get all the results which cover all the needs for all these specific columns with certain different small load cases. You have possibility to set up certain parameters. You can define your system. You can drive, as mentioned, your load correction. I know, thank you. You can drive your load connection and your connection between your elements. And at the end of the day, you can do the code checking. And for sure, as also Carsten from Armin mentioned, we can now transfer these results back to Revit to do, for example, reinforcement, design, and modeling. Which you can see here now in this slide here. We have at the left-hand side again such a subsystem or a system where you can define how the load is transferred from top to bottom. Also here we see different load takedowns for this corbel as example. And at the right-hand side maybe you can get the proposal of your reinforcement generated automatically from your design. And in the middle of this sheet you see the drawing generated with our reinforcement drafting tools automatically out of the 3D model inside of Revit. So what's my conclusion out of that? As I mentioned in the first slide, we have many possibilities to do structural analysis. And it's now the choice of our structural engineers to define the right way, or maybe to doing analysis in more ways, combining results to each other, understand which are the results which might be right, because it does not exist the right result. Maybe we have to differ also system for different analysis types. So maybe for different load cases, we need to change also our system or our concept. And I think, in my eyes, the building manager is quite simple to the manual calculations, because years before, where we have done manual calculations, we have done the same thing. We have extracted a subsystem, We have thought about the supports of this subsystem. We have thought about where the load comes from, put that load on your subsystem. And this we like to support now with this module Building Manager to give you a completely new possibility inside this BIM environment to do what you like to do. So thinking with your engineering brain to understand construction and calculation. And also this means that I think this is the simplest one. So comparing to the 3D analysis where it's quite hard to understand the results, to read out all these numbers from your 3D system. So therefore I think it has many advantages to implement such a workflow in your structural analysis. And one of the best things is you as a user has the flexibility and you are able to drive the behavior of your structure as you have the possibility to influence your load takedown. So that's all from my side. I like to thank you. Spasiba, and hope enjoy your rest of the day.
Спасибо, господин Дариц. Прошу не уходить.
Thank you, Mr. Dariz. Please don't go away. Questions?
Thanks for your presentation. If I got you right, so maybe I'm mistaken, if I got you right, so this new visual programming language will give us, construction specialists, the freedom of delivering or changing the structure as we wish, right? So the question is it a step of statistic to generative design? So I turn into not a construction specialist, rather than a programmer.
Yeah, definitely. So I'm not sure whether the interface looks like, because this is definitely our first ideas and the first steps. Huh? But definitely we like to give engineers more tools to influence and drive the results of analysis. Huh? So that's what we'd like to give the user.
And the next step will be generative design, right?
Possible, yeah, possible.
Okay, thanks.
Тольятти, пожалуйста.
Hello, I'm Alexandra from Tolyatti. You spoke about the future and you said that engineers will get freedom in choosing the behavior of the structure. But when we have the freedom of choice, the risks increase and human factor increases too. So, speaking about the future, what do you think? Is it possible to let Sophistic evolve to such a way that it thinks together with the engineer and gives prompts to the engineer and suggests that the chosen way is not the optimal one? So, some hints and tips.
Very good question. But I think that it's also a problem if we let the computer do decisions what we should decide as a structural engineer or as a human being. So therefore, it could be a problem if you as a human being do some mistake, for sure. But I think it's more, or it's the worst case, if we insert some data in the machine do something magic stuff, and we get out results without thinking on that results. So I think that's more critical than give you more influence, more possibilities to influence your calculation. Okay?
Спасибо. А еще вопрос?
Thank you. Any other questions? And if I may, I have a question. Mr. Dariz, you mentioned in your presentation that your software is getting closer to 100% representation of loads for walls and slabs. Does it mean that the software has some accuracy, non-accuracy range, a certain accuracy range? So what is it? 95% or 99%? What is the error, the probability of errors? What do you think? 1 to 10, 1 to 100?
So generally, when we talk about structural engineering, definitely I cannot speak about 100% correct results. So if I'm a mathematical guy, for sure 2 plus 2 gives 4. That's quite sure. But if I give this question normally to some structural engineers, so what's 2 plus 2? I'm quite sure that all of you gives me different answers. And the answers may vary between 3.5 and 4.5. And now you ask me about the range. It's quite hard for me to give you an answer on that question. I think the range of your accuracy of the results, it depends on your model. And as you guys to influence your model with this load takedown and with the type of your model, you have to be, it's your decision how accurate your model is. But I don't know that if we can give you a number of the accuracy of the model, because if we can do that, we have the 100% model in behind. And then when I have this, I can give you that number. But we don't know about the exact physical model. Then we have to talk about exact physical 3D calculation with non-linear and phase elements. Then we have to talk about 3D brick elements and do a very physical calculation of the model, which is quite tricky.
Спасибо. Есть ли еще вопрос, господин?
Thank you. Any other questions? There are no further questions, so thank you.